поверхности. So this is the title of today's lecture. Any questions about the previous lectures? Let's have the sheet. So it is unthinkable to cover the first part of the title in one lecture, in several lectures, or in one semester course. As perhaps everybody knows, the foundations of Grothendieck scheme theory were formulated in many volumes of Grothendieck's non-finished, many-volumed great treatise, Design de géométrie algébrique. So first of all, I assume most definitions and constructions known, and I'm just going to remind them a bit. And secondly, from this ocean of concepts and definitions and results, I extract the ones that are needed for our main subject, arithmetic surfaces. However, I start with some generalities, some discussion of what is a manifold and generalizations. And our general point of view will be in considering the opposition of them, such objects embedded versus abstract. This topic deserves some historical overview, so let's turn our attention to 19th century, where the greatest mathematicians contributed a lot to the basic idea of manifold. Let's start with Gauss, who was doing differential geometry, or we could say developing the subject of differential geometry that in his time was mostly the geometry of surfaces embedded in the Euclidean free space. And one of his results was what he called the theorem. Sorry, I'm not sure in the Latin spelling. In egregium, I'm sure. In theorem, I don't know, sorry. Egregium. And moreover, I've forgotten whether it means golden or silver theorem. Does anybody know Latin enough? But I know the formulation. so it was just about Gaussian curvature that was originally defined in terms, may I write something a bit non-trivial, of Gaussian map. That associates to every point of a surface the unit normal. Well, the surface is supposed to be oriented in the free space. And the main curvature that was just defined as the determinant of Gauss map seems to be a purely exterior constant. However, Gauss has found the inherent definition of it, and that was the nature of the theorem egregium, as Gauss has formulated it. By the way, he was thinking about these subjects during his practical geodesical work somewhere in Germany. And his formulations, as far as I understand, the first formulation in terms of the abstract geometry was as follows. He has understood that one can compute the Gaussian curvature using measurements only on the surface, without any use of the external structure of the embedding of these normals. Technically, this result is just the expression of Gaussian curvature in terms of the metric tensor, and in this form it was widely generated by Riemann. Well, I will write the curvature tensor just using the standard notations, one upper index and three lower. Now I assume that you know what it is about. Of course, the tensor definition, the coordinate definition of it is terrible, and it's not differential geometers usually don't remember it precisely. However, there exists an invariant definition in terms of operations over vector fields. That I omit. I just say that it has some deep geometric meaning, also inherent, but one of the great Riemann steps was the generalization of manifold to any dimension, together with the Riemannian metric. And there was another another great idea of Riemann that is perhaps closer, to the algebraic geometry. So here we have Riemann tensor, and then we have the concept of Riemann surface. Again, I assume that you know what it is, and originally it was closed to the embedded mathematics, that is, just studying integrals of algebraic, as people said, and functions. We know that it's impossible to integrate functions, we integrate forms. So he had a geometric idea of, I don't think I draw it in a clear way, but I believe that you know what I'm trying to draw. So he worked with the analytic continuation and the mathematics of finite valued functions of complex variables. So this is close to the embedded geometry, and it can be made quite strict, just introducing another axis and thinking about Riemann surface as about plane curve. However, again, Riemann's great idea was to consider this object as it is, and we know what an abstract Riemann surface is, and Riemann was the first to define the genus that for some time was called the Riemann number of the surface. And the third great mathematician of 19th century, whom I'm going to mention, of course there were more people who contributed to the development of these ideas, was Poincaré, who defined the manifold in the sense we are using now, as a smooth manifold, and again he started from the concept of embedded manifold. So from it was the initial point, from the embedded manifold to the abstract one that we are going to reproduce soon, to the abstract. Now I just write symbolically what everybody perhaps understand to some extent. So in the second half of the 20th century, the manifold was defined as a pair of topological space and certain kinds of sheaves of functions on it. And this is the idea, the development of which we are going to discuss today. Any questions about what was said up to now?
About the picture for the Riemann surface. What do you want to show for that coordinate?
By this picture?
Yes.
Well, as Riemann formulated it, it was something spread over C, like well, the square root of well, z squared minus c. So with these ramification, with these generally two sheets and ramification points going around which you find yourself on another sheet. So in his text it was, I have read carefully the English translation of it, of course it was written in German. It is highly informal, but as I said, you can just, for example here, instead of thinking about square root as about two-valued function, you just can introduce another excess. But it turned out that a much better idea is to consider the same object not embedded at all, but just as an abstract surface with the structure sheaf that in this case means the sheaf of complex valued holomorphic functions, according to the best language for it would be the functions satisfying the Cauchy-Riemann equations in any local coordinate. So, as you see, in all the three cases, we see some interaction between the embedded manifolds and abstract manifolds, and in fact, we are going to continue in our course, we are going to continue this relation, and up to now in the first two lectures we in fact discussed the embedded algebraic varieties, just as the sets of solutions of some polynomial equations. Though we have generalized it in some direction in such a way that the solutions took their values in variable fields. However, the general idea of the algebraic geometry we have discussed up to now was the idea of embedded algebraic varieties. And now today we are going to switch to the abstract ones. Any other questions or remarks? Good. Oh, good. Yes, somebody seemed to participate. Well, then we continue this discussion, turning to the 20th century. As it is not so well known as it should, Grothendieck has predecessors was preceded by the mathematicians from seemingly distant domain of algebraic geometry or theory of manifolds that was developed mainly here in Moscow by a great mathematician in the Radical Fund, and Naimak, he is a sister and a sister. So they basically they worked in functional analysis, and I'll define precisely what they were considering, because the intuition they developed is basic for the whole theory of schemes. So they considered, to begin with, quite an abstract, compact, space. And let me think for a while. Seeing not all x, that is just the set of continuous functions are, well, I remind our agreement that by default, when the two objects are assumed to belong to the same category, here it is the category of topological space, then this the arrow means a morphism in this category, here the continuous mapping. Now let me think for the appropriate notation for it. Well, let it be simply B, and it is a Banach, Polish mathematician algebra. That means that it is just an abstract algebra, that is the ring containing constants, that is just the real numbers there. But to be Banach, it means a norm, when say norm, let's think about the appropriate letters, maybe F. That is the maximum value of absolute value of f of x. So no assumption on the regularity of x, and there is no concept of regularity, because it's just an abstract topological space. Is we write maximum and not supremum because the continuous function is bounded on any compact and assumes its maximum value somewhere. So the great idea of 30s, all of it happened 30s in here in Moscow, was that said theoretically x is in one-to-one correspondence to what we are going to call in a bit non-standard way max of B, max of B, like this. That is the set of picture. Suppose X is just a segment, then there B. Well, perhaps I better write the definition of this one-to-one correspondence. So, well, this arrow is defined in such a way that the X naught is mapped to the set of F of B such that F of X naught is 0. And now the picture is appropriate. So if this is X and there is a point X0, X naught, then the corresponding ideal to it is just drawn symbolically here. Intuitively, everything is clear, but perhaps the construction itself deserves some thinking about it, and the precise formulations and proofs. Саша, добрый вечер, слышите? Clear, but some person from Paris seem to have appeared here. So the main impact of this series of work resulted in the understanding of the very deep relation between functional analysis, that is a matter of studying such objects with some special axes, not just compacts, but, well, X being a circle leads to the harmonic analysis and so on. And it turned out that such an abstract subject as algebra itself, with its rings and ideals, is quite relevant in studying functions. Perhaps I want to find some places to formulate some pre-graphic and maybe too strong expression, like so any element, no, not any, but perhaps elements of a ring. Sometimes it's useful to forget that our rings are algebra. The constants are not always so important to be kept in mind. So elements of rings are something like functions on what we do not specialize it. And the mathematics of the 20th century had to wait for Grothendieck to answer this question completely. So, any questions about this story? May I repeat that it's not going to be used mathematically. This point of view is not going to be used mathematically, but is going to be used psychologically. So, then I erase this story, and we turn to the pure commutative algebra. So, now, sorry, I don't remember whether we have agreed, I believe we did, to denote the category of rings by three first letters of the French word unknown. So this just means that R is a commutative ring. And to answer this question, we have to decide. So R just given an abstract ring. Again, it is to be considered as a function on what? Now, Gelfand Neimer would suggest that this double question mark is just the set of maximal ideals of R, and at least for some rings, such as functional rings, this works perfectly. However, the notion is not so good because, unfortunately, it is not functorial. Namely, if we have a homomorphism from R to R prime, and and we have a maximal ideal in R prime. It's better to put prime here and then this is the traditional Gothic maximal idea of R. Then the natural attempt to associate some mapping of the points on which these rings are supposed to be functioning would be the inverse preimage. See, mu yes, we would like to put it, but the trouble is that the preimage of a maximal ideal is not, can be not a maximal ideal in R prime. For example, What is it? For example, if R is U and R prime is Z, then there is the only maximal ideal R as in any field. It is the zero ideal. However, its pre-image is zero, but zero ideal is prime in Z, but not a maximal. 1, 2, maximal idea or the maximal ideal in Z, because it belongs to lots of larger ideals generated by any numbers. So this idea doesn't work in terms of establishing the functorial correspondence between points and functions close to the Wittmann-Neimark construction. And in order to curve it, or saving and at the same time extending the idea, is introduce what everybody is supposed to know. Spectrum of R, that is the set of primes, ideals, also try to write Gothic letters, and as perhaps everybody knows, that any remorphism R to R prime to R results defines the inverse mapping from spectrum R to spectrum R prime. I think we better usually write brackets, though it is not traditional. Just sending the any prime number to its ray image. And it corresponds to the intuitive picture of pullback of the functions. If there is no questions about what is written here, I'll try to fix the intuition connecting these objects. And well, I would say that at least spec spectrum on this point is a co-functor from unknown to, as it is defined, it is a functor to set, but as everybody is supposed to know, the spectrum of a commutative ring carries the Zariski topology, according to which this is a functor from commutative rings, from the category of commutative rings to the category of topological spaces. Now the intuition is as follows. Just try to start with these spectra. So denote, say, X as spectrum of R and X prime the spectrum of R prime. And then as soon as we have if R prime is something like functions, well, functions, let's write it this way, X prime 2, let's see, one question mark, and R is the same function like this. Then what we have is, so here is X prime and the question mark here, and say F here, and if we have something like alpha, how do you call it? Who pronounce the English for this character? I'll find it out. So cardinality. So, and we have X here, F prime here. Then the F being the F is simply the pullback of F prime. That is F prime composed with alpha prime. So this is quite a natural set theoretical construction that relates points and function, and it works, this picture works in different nine-mark mathematics, but it also almost works in algebraic geometry we have discussed. And whenever we consider, say, R or R prime not as abstract rings, but as the K algebras or over a fixed field K, and if our x's and x primes are not arbitrary, but they affine varieties, that is, subsets of affine spaces defined by polynomial equations, then the picture makes sense and is consistent with the intuition of mapping of the topological spaces and corresponding pullbacks of rings of functions, but with an important novelty. Now let's introduce some notation. Now let us consider an ideal and say K X sub n, then the corresponding now what we have defined in the previous lectures, we have defined the set of generators of an arbitrary ideals. So say if A was generated by a set of polynomials, then R is nothing but the corresponding R is nothing but the ring of polynomials factorized by the ideal defined by the equation, and it is considered as a so it is ring of regular or polynomial functions on the affine variety. Our variety was denoted as the value of the functor, point functor, this underlined O K. Here we assume that K is algebraically closed. So though we have not discussed it, but the whole story of the category of affine varieties and their mappings can be developed easily. So we have to decide what is a mapping of the affine varieties, and there is the natural idea that it is just defined by polynomials. Component-wise, the embedded affine varieties are mapped to each other by polynomials. I haven't yet disclosed the novelty. So as soon as we think about varieties, affine varieties as about, say, curves or surfaces or something like that, as for the curves, there is almost nothing new. Here are the maximal ideals. So any point, as in Gilpin Naimer correspond to, let's give it a name, P corresponds to the ideal and P in maximal ideals. maximal over, well, here we have to write down the whole construction. So, exactly as in Gilpin-Weimark, the points of the curves correspond to maximal ideals. However, as for the novelty, here I have to erase what was said before in the abstract setting. Even in the set of curves, in such picture, there is no place. Let's think about a curve and points on it. The points correspond to the maximal ideals, but there is no place for the zero ideal, for the ideal zero, consisting just of zero. It is an ideal as soon as these ring of regular functions does not contain zero divisors. So there is no place for zero. In this case, zero ideal belongs to the spectrum, or we have the notation for R. And it is not so easy to imagine it. The suggestion is to think about a thick point. Well, since I assume that everybody knows the Zariski topology, then there is such a non-classical element. The point is thick, and anyhow, everywhere dense. However, the intuition still works, and in many questions we can ignore this generic point of the curve. Things become a bit worse from the intuitive point of view when we move to dimension 2. So let's just try to imagine the spectrum of polynomial rings, spectrum of k of x, y, or any other surface, but let's think about the simplest surface in the world. So we have a classical plane like this, and the points on it correspond to the maximum ideal, correspond to maximal ideal of this polynomial rings, but any irreducible curve defines is a point. Is a point corresponds to the polynomials that are annihilated on this curve, and one has to train his or her imagination to think about such an object as, again, about a point. A point whose closure, it is non-closed in the Zariski topology, and its closure contains all the points on it. So we have a kind of very non-classical topology here. However, the advantages of this Grothendieck picture is that it is universal, abstract, and functorial. Now, sorry, I was going to assume all of it as known, but perhaps this reminding together with the picture was not just a waste of time. Anyhow, we are going to use this intuition. However, maybe let's consider the last important standard point. Well, I'm not asking about your questions since I'm already raising everything. So let's discuss a bit, try to discuss again for R a commutative ring, whether following Dilfan Naimark we can think about R as a set of functions on its spectrum, or R with some values. And one of the striking points, well, let's first of all, let's give let me remind you some precise construction. So suppose we have a prime ideal spectrum R. Now I'm not going to use a very standard notations or postpone introducing it, but just introduce two ways to associate the quite a definite P to B. The first one, take R over P. Since P is prime, then this factor has no zero divisors. As soon as it has no zero divisors, we can take the fraction fields with the field of fractions of the factor. And please think about this isomorphism if you are not very used to it. There is another way to the same field. That is, we take the local to every prime ideal, we associate the local ring. That is, it is defined as so there is a multiplicatively close. The other definition of the of an ideal to be prime is that the complement to it is closed with respect to multiplication, or this this complement is a multiplicative set. Then, with all, as with all the multiplicative set, we construct the set of fractions like this, defined just in the same way as we construct usual fractions starting from integers. And then it is a local ring that contains the only maximal ideal. Perhaps I write it without any abbreviations and additional notations. Again, it is a small theorem from commutative algebra. Well, I'm saying small because it is simple enough. Maybe I give the general recommendation. Please read Лекция, which is a perfect reference for any questions of commutative algebra. So this is a local ring, and it contains the only maximal ideal, consisting, of course, of the fractions in which the numerators lie in the ideal. And the factor over them is the same, gives the same field as constructed by another way. And now the thing is that to any element R in our R capital, we associate a value. So I'm writing the question mark. It is something, so it associates what is the best way to define it. It is, well, the class of our modula P. It is, that's the numerator, yes, the class R modula P over 1. I'm using the first definition here. So in this way, any element of a commutative ring becomes something like a function. So to be more precise, it is defined over all the functions like that. Well, I'm afraid I have to introduce the standard notation. Looks like this. The whole residue field. So it is a value on P in the residual field. So it is not a function in the sense of Gelfand-Naimark, and not a polynomial function as it can be understood in the case of K algebras in terms of polynomial equations. It is something different, but not so complicated as one could think. And let's turn to arithmetic, that is to the basic case when our ring is just the ring of integers. Then we draw spectrum of R as 2, 3, 5, 7, and so on, and at the infinity in such a way that here are, the infinity corresponds, I'm always going to underline infinity, meaning that it is rather a point than a quantity. So infinity corresponds, of course, to the zero ideal, or sometime I'll put it in braces so that we cannot think that it is an element of a ring or a field. And here we have the picture of a function that assumes values in different fields depending on their arguments. Okay, let's write down that in our notations. K, the residual field K. Here I use the usual prime, and of course it is just Z over P Z. That we once forever denote by the only field of P elements, and of course K infinity is just Z, the fraction field of Z over 0, that is Q. So I'd like to erase everything, but it seems that all the pieces are valuable. So let's perhaps just draw, say, 120 and something like a function. Z to we don't know what. So we think about the graphic of this function that has that can be given quite a precise meaning. So what is its value in what is the value of 120? We have to decompose it. So it is 8 times 15. Is it correct? Yes, it is. So cube. So it assumes the value 3 here is the point of the graph 1. Oh, sorry, no, 4 was 1. Here, and that's all, as every number it is finally supported and over the infinite point, it just takes the value 180.
So what is the vertical axis then?
The vertical what?
Axis.
It is just to mark. Yes. Oh, thank you for your question. Yes, this is perhaps this picture is appropriate only for some future considerations. So as soon as it takes its value, or no, it's just wrong. The sense of this I have to correct everything. So we use this meaning. The values in the vertical line are really we count it as 0, 1, 2, 3, and so on, but over 2 the function takes value in the field of 2 elements, over 3 in the set of 3 elements, over 5. So its elements are here 0, 1, here 0, 1, 2, 0, 1, 2, 3, 4. So in this case, this function is, sorry, I've drawn quite a wrong picture. So it has, this function has its zeros in 0, 3, 5. Now as for 7, we have to calculate it, and 120 modulo 7, we have to calculate. So this function is very far from being finally supported. Thank you very much. On the contrary, it has just a finite number of zeros. 119, I guess, is 70 something. 70 plus 49, is it correct? Yes, it is. So it is 1 modulo 7. So here our function is 1, and it will have no more zeros, no more divisors. So please forget about that wrong big picture, and sorry for having drawn it. So the graph of this function it consists of the residues. And we are going to train ourselves to work with the interpretation of our functions like this. And as soon as we turn from Z to the rings of more complicated algebraic numbers, the pictures are also going to become more complicated. Any questions about what is written and drawn now? Okay then. Now perhaps we can erase these verses, this opposition, since for some time we are already discussing only the abstract version. Now let's just repeat the basic definitions of Grothendieck theory, and the starting one is the ringed space. And I use the shortest definitions. So X, it is a pair X O X O, where X is a topological space and O is a co-functor from the set of open sets to the commutative rings, so that it associates to every open set U is the naturally denoted ring O of U. No tricks. The only trick is that sub x behaves like a category, and it is a small category defined by the set, by the partially ordered set of open sets in X. Every partially ordered set defines a small category. So so we just say that ringed space is nothing but a functor. To be quite sure, we denote another notation that is for U and V being the open sets in X. Whenever one is contained in another, or maybe coincides with, we denote there is a, since it is a co-functor, I used a bit non-standard notation for it. Then we have the inverse mapping, inverse morphism of rings, that is O over V, larger, from larger one to O smaller one, and well, it is usually denoted like this. So this is a ring morphism, and the letter rho is explained, is the first, the Greek version of the first letter of the word combination restriction map, or morphism perhaps that time. perhaps we better keep in mind still the defunct Lamarck with the functions on the segment. Here is the larger interval, here is the smaller interval, and there are lots of restrictions from the functions on the larger one to the functions on the smaller one. This gives the appropriate intuition. Now, perhaps the last thing I have a time to pronounce today is a bit not standard one. I would call it the Grothendieck relativity. Has nothing to do with Einstein relativity. I mean, in the essence of this concept, but it means that instead of considering properties of geometric objects, so from now on, all our geometric objects will be the pairs, the ringed spaces with the appropriate restrictions, which we are going to sometimes to impose and sometimes to impose not. Forget, as Grothendieck tells us, advises us, forget about the absolute properties of geometric objects. Consider arrows. Consider arrows instead of points. And Grothendieck was the first to draw arrows not from left to the right, but from top to the bottom. So sometimes, well, perhaps not today, sometimes we'll denote, as everybody in the world, these pairs by the unique letters, but basically, yes, just I use the letter B not as a random one, because B is the first letter of the word base, and often we are going to consider variable objects over the fixed base. One can say in a very preliminary way the geometry, the arithmetic first. No, first geometry. Geometry is the set of things O, X, over such a funny thing, maybe over just one point, think about one point, but this point is going to be the spectrum of a field, of say a fixed field. This concept seems funny enough because there are no they are close to no ideals in the field, but in fact there is the only ideal, the 0, 1. Therefore the spectrum of a field consists of the only point. But we are thinking categorically, and we should remember that together with any object, we are considering all the arrows. This time, this is the group of automorphisms of the field, and it gives quite a rich structure to all the objects over spectrum of K. And once in every mathematician's life, all the axioms have to be checked, so that to be sure that this geometry is nothing but the algebraic geometry over the fixed field. And this is the picture, and I have to find the place to write down what is arithmetic in this very preliminary explanation. Arithmetic is considering x. So x over speaks the spectrum of z that we have already discussed. This is a general context for developing the geometric definitions. I hope I can erase almost everything here. No questions about what?
Do we need to say something about sheaves here and not just pre-sheaves?
Sheave here, well, in this preliminary way, we consider just any ring space over spec Z, but I have not yet given the definition of arrow. So the definition in the category and the category of ringed space was not defined, and we do it now, and then the definition will be automatic. So by the way, we are not going to consider the whole category of all the ringed spaces for the reasons that I hope will be clear soon, but just discuss what is an arrow from X. O, X, to X prime. Well, there was a prime before, let's use another letter. Yes. So this is a very general definition, a very general concept. So it is a pair. But let's say well, I just write the neutral word arrow. What does it mean? It is just a pair sorry, this F dies, well, switch its position. So it is a pair of mapping on points. Since they are topological spaces, the mapping is assumed to be continuous. And now for any open set in Y, so open Y, there is an F, I think it's dies. The name of the character is perhaps dies, I'll check before the next lecture. F dies sub V is the ring morphism from O Y of V to O sub X of F inverse F pre-image of V. Again, I should say that in the basic case where we are working with rings of functions on topological space, this F upper dies is nothing but the standard pull back. As for the axioms, we can avoid them. Of course, I could spend my half an hour to write all of them, or just not axioms, but of course it should be all the system of ring morphisms should be consistent. Consistency. But I can avoid it simply saying that this O and this O are functors, yes, from the ordered sets of partially ordered sets of open functions, one to another. So this is the consistency follows from the general notation of transformation or nations of functors, or maybe small functors. And here you see, perhaps, some of you perhaps see the reason why I don't consider the category of all the ringed spaces. We could do that, but it would be more naturally to consider it as a two category, because basically the objects of these categories are functors themselves, and the formalism of two categories exists and is, well, beautiful for some people, but rather messy, and it is not the subject of our considerations. Any questions about this? By the way, one of the reasons to consider objects in such a crazy generality is that the easiest some easiest definitions are given in the most general settings. Of course, in the true algebraic geometry, we are considering by no means the arbitrary ringed spaces, but spaces with restricted by lots of properties. However, some definitions do not demand any properties, and it is easy and shorter to consider all of them. I was going to give several basic definitions in this language, but I have no time for that, and I just relate the concept of Grothendieck relativity to the methodology of giving definitions. So, instead of, it follows from Grothendieck relativity that instead of properties, it is of objects. Now, our objects are going to be schemes. Schemes are just, well, let me pronounce it orally, because this generality just gives us the possibility to give the basic definitions just in word formulations. That's why I am not writing it down on the blackboard. And just what is a Grothendieck scheme? We better define the whole category of schemes. Schemes are the ringed spaces locally isomorphic to the spectra of commutative rings. This is the definition of the great object of great generality that can be put in a rather short sentence, and we are going to choose the part of it related to our course. As it often happens, the goal of our course is by no means the general theory of schemes, but I just fixed some notations, as I said in the beginning of today's lecture. So instead of property of schemes, there are hundreds of properties of morphisms. Usually we, as I said, we fix bases, and then apply the Grothendieck relativity. So they are, sometimes affine and projective. Here we have the obvious absolute analogs of them. Now, the projective morphism is related to the embedded manifold, as we have discussed today. But there is a proper morphism, the ranges of which I'm going to define it the next time, are something like abstract but complete varieties. And then there are open morphism and closed morphism, and lots of others. And there is really a much more difficult object that I was going to start discussing informally, but it would be useful if I'll just ask all the participants about their acquaintance with the concepts of flat morphism. And well, this is perhaps all for today, and it just relates this lecture to the following one. Now, please raise your hands, those who know what moduli over a fixed string are called flat. Almost everybody. Does it mean that you know the definition and the properties of the function tor? Perhaps you know the official definition related to the function tor.
I wouldn't say.
What are the... okay, well, we are going to discuss it the next time. So I'm going, just as a plan for the next lecture, we are going to specify the concepts of general scheme theory that are related to arithmetic surface, and all of them are simple and very clear geometrically, with this one exception. We are going to consider flat morphisms, and well, I'll give the precise, of course I'll give the precise standard definition, but it is, to the best of my understanding, it is only partially intuitive. We'll see in a week. Any general questions or suggestions or comments?
I have a question, but it may be personal, about, well, varieties over algebraically closed field. So, can we say that a function has the same value at two different points?
Yes, yes. If we work over, in the critique sense, over the spectrum of, in fact, any field, not necessarily algebraic values, then the functions, the values of functions in the maximal ideals take their value in the basic field, as in the most classical case.
And so the fields of fractions are all the same.
Yes.
So, like canonically, I think.
Yes.
Okay. I will need to think about this.
Other questions? Okay, then thank you for your attention.